All right, so here's where we left off in the last video. The idea that we've been working with up until this point is that we've been integrating functions over plane curves, C. So that's how we've been defining our line integrals up until this point. But what we want to do is extend that idea into space curves. What if we have a function of 3 variables and some space curve C in the domain of that function? Well, we define things very similar to how we define them in the case of a plane curve. The line integral of f of xyz ds over the space curve C, and I'm going to assume that the space curve is given parametrically in this form: r of t equals x of t I, y of t j, z of t k. We substitute the x, y, and z's of t's into the x, y, and z here. That's what you're seeing here. And then we multiply by ds, our arc length differential, which becomes this in the case of a 3 variable, in the case of a space curve as opposed to a plane curve. So it looks very similar, but we just pick up this extra variable and this extra term here in the case of a space curve. Now this notation gets really, really cumbersome, but if we choose to use vector notation instead, it can make this much more compact. So for example, if like I said, if this parametrization is represented as a vector function the way that we're doing it here, r of t, then this thing in here, this x of t, y of t, z of t, can be more compactly notated as just r of t. So it's like plugging r of t, a vector, into the function f. Similarly, this quantity right here should look really familiar. This, in chapter 13, we showed was equal to the magnitude of r prime, again when r is given in this form. So I can represent this line integral much more compactly this way, and this would also apply in the case of a plane curve. I would have r of t equals x of t I plus y of t j. In the plane curve case, would still reduce to this in vector form. Worth noting also is in the special case where the function f of xyz is the constant function 1, then this integral reduces down to just this, the integral from a to b of, and again, we're assuming that interval a to b is the parameter interval that gives us the curve that we want. This we know to be the arc length of the curve C. So that special case kind of confirms something that we've seen previously, which was that this reduces to arc length. Okay, and then finally down here at the bottom, we also define line integrals over space curves with respect to x, y, and z, similar to how we did before. If you see something of the form, the line integral over a curve C of a function, and there's a dx here instead of a ds, then instead of using this guy right here, our dx just becomes x prime of t dt. And as before, we more frequently see line integrals with respect to all 3 of these variables simultaneously for these different functions, p, q, and r here. So this is defined in a manner similar to how we defined the case of a plane curve. So let me take a look at an example here. I worked this example out ahead of time. So we're just going to take a look at it. In this one, we're evaluating the line integral, where the function is y, or the integrand is y dx plus z dy plus x dz, and c is given by this parametrization right here. So there's a good amount of problems in the book where you're given the parametrization from the very beginning, and those are kind of nice because a lot of the times a decent amount of work goes into just finding a parameterization in the first place. But we're given this. Now we're going to be turning this into a definite integral after making a bunch of substitutions. So y, z, and x are all given to us right here. dx, dy, and dz come from the derivatives of each one of these, x prime, y prime, and z prime, which I found here. These are all very straightforward derivatives to find. So what I would need to do is take all 6 of these things and substitute them where they go in this integral, and then look at it as a definite integral from 1 to 4, since that's my parameter interval. So that's what I did here. substituted, t in for y, dx was 1 over 2 root t. If you multiply t times this, it simplifies to 1/2 root t. I did the similar substitutions for the other terms here. And kind of going along with my theme of keeping these videos from getting too long and spending a bunch of time on the tedious Calculus 1 and Calculus 2 stuff, I'm not showing all of the steps in doing this definite integral. This is actually a Calculus 1 integral. Oh, I felt like I had to sneeze. This one comes out to 722 over 15. You can verify that by filling in the gaps, but it's not really worth the time to go through that part right there. All right. So the last part of this section concerns line integrals of vector fields. Now, up until this point, the line integrals that we've been talking about, whether it's over plane curves or space curves, they've been line integrals of functions that look like this, f of x, y. These functions, even though we haven't used this terminology in 16.2 yet, these functions are scalar fields. Remember, scalar field is an alternative term for the types of multivariable functions we've dealt with before chapter 16, because the outputs of these things are scalars. So really, what we could have called these are line integrals of scalar fields along a curve C. What we want to do now is take a look at what would happen if the integrand wasn't a scalar field, but was a vector field. How can we give a meaningful definition to a line integral of a vector field? So that's what we're going to do here. And the motivating thing here is going to be work. You've already seen through Calculus 2 and a little bit of what we did in chapter 12 of this class as well, that the concept of work is it kind of coincides, or it can be found as an application of integration. Calculus 2, you really talk more about that, but what we want to do here is consider the work done. Well, first of all, let's go back to the thing we talked about in chapter 12. If you have a force and it's given as a vector, so it has a magnitude any direction, and that force moves an object from point P to Q, and if we let D represent the displacement vector PQ, then we showed back in chapter 12 that the work done moving that object by that force is given by F dot D. It can be evaluated as a dot product. Okay. What we want to do is use that idea to consider how we might compute the work done by not just a single force, but a vector field, where every vector in that vector field represents a force acting in some direction. So really it's a force field, like what we talked about in 16.1. We want to consider what is the work done by a force field moving a particle along a curve, a space curve in this case, and we want to define our line integral to be something that accomplishes that. So here's how we go about this. First of all, let's suppose that we have a force field, and to keep things general, I'm going to call it Pi plus Qj plus Rk, P, Q, and R being the components of that force field. It's continuous. We're going to make that assumption as well. What we want to do is compute the work done by F, our force field, moving the object along this curve C right here. So, and it has to be a smooth curve for this to work. So we're going to start out in a way similar to how we define the line integral at the beginning of this section. We divide our curve C up into subarcs by cutting up our parameter interval into equally sized subintervals. And then in each of those subintervals for our parameter interval, we're gonna choose a sample point, which is going to correspond to a single point in each subarc of this curve. Now, what we're going to use that point for is we're going to compute two things. We're going to look at the unit tangent vector to this curve at that point, as well as the value that we get in the force field by plugging that point into our function f here. Okay. And then if you notice, these two vectors represent those two quantities for this arbitrarily chosen sample point. Now remember, the by definition, the unit tangent vector has a magnitude of 1. So if you multiply it by a scalar, then the magnitude of this new vector is going to be the same as whatever the absolute value of that scalar is. So what I want to do is use this unit tangent vector to approximate the displacement vector in moving this particle from the first point, the left endpoint of that subinterval to the right endpoint, or the first one of the endpoints to the other, I guess. Now, if this is a smooth curve and you cut this thing up into enough subarcs, those subarcs start to look linear, and so that scaled tangent vector is a good approximation for the displacement vector when we have enough of these subarcs. Okay, so that would look like this: delta SI, where delta SI represents the length of the subarc, times my unit tangent vector at that sample point. Okay, so using this, if I wanted to approximate the work done moving that particle not through the entire curve quite yet, but just from one point to the next in one of these subintervals, or subarcs. So basically, I want to approximate the work done moving this particle across just one subarc. Then I can use these two vectors and take their dot product, f dot t, which is our approximation for d. That would look like this. And remember, scalars can be brought out of dot products like this. Okay? Now, if I were to do that for all of the subarcs that I cut this curve C into and then sum the results, that should give me a good approximation for the total work done moving that particle through C. So that's what this sum represents. And based on that argument, again, if we let the number of subarcs for this curve go to infinity, we expect this approximation to become exact. But this is a Riemann sum, so it leads to this integral. Okay, which we drop the x, y, z just to keep things brief or to keep things compact, and we oftentimes write this integral as as f dot t, the integrand, I should say. Okay, now this is a useful definition for the work done in the line integral over this force field. For the intuition, it gives us an idea of where this result came from. It's not very practical for computational purposes, so we're going to write this in a different form. If the curve C has this parametrization, r of t equals this, we know from the work that we did back in chapter 13 that the unit tangent vector is really r prime over its magnitude. Okay, so if I make this substitution for t right here, and then in addition to that, if I use the fact that ds is the same thing as the magnitude of r prime dt, so I make that substitution for ds as well, you may notice that I get some cancellation happening here. The magnitude of r prime cancels with itself up here, leaving me with f of r of t. Well, I can write that here, f of r of t dot r prime. It's typical to take this r prime of t dt and just call it dr. So this is the notation that you're going to see most often. The line integral over the curve C of f dot dr. But this is what it means, okay? And it's equivalent to this, which is where we got our definition for this line integral. Okay, now we did this from the context of work and considering our vector field to be a force field, a continuous force field, but this actually is a useful definition for evaluating a line integral over any continuous vector field, even if it doesn't represent a force field. So this is what we use as our definition for the line integral of the vector field f along C. Okay, all right. So just a little bit left to cover, and in fact I think I'll do the last part of this in the next video.